In Part 6 of Lecture 2, we will take a look at special problems in lexical analysis. There are a few other problems that we may face in lexical analysis. One is token overloading, where a given symbol may have more than one meaning. Backtracking, where we will have to go back and scan something all over again. Buffering, going through the process of saving text in the input stream that we have not yet used. And lastly, the situation where keywords in the program are not reserved and can be used for other purposes as well. On occasion, we may run into a difficulty presented by a lexeme that may serve more than one purpose in a programming language. For example, in the programming language BASIC, an equal sign can be the test of equality and also the assignment operator. This can be handled by using different lexemes. So, for example, in C and in Fortran, a single equal sign is used as an assignment operator. But the test of equality in C is two equal signs, and in Fortran it's period EQ period. Pascal takes the opposite approach, where equal sign is the test of equality and colon equals is the assignment operator. If several lexemes are grouped into one token, it may become necessary to separate one or more of the lexemes out to become a distinctly different token. In rare cases, it may become necessary to backtrack and scan the part of the text of the program all over again. One classic example of this is in Fortran. Back when Fortran was developed, programs were put on punch cards, and the key punch operators had a reputation that was well earned, supposedly, of advancing to the right column to print the data on it, but then not necessarily placing the blank spaces in that belong there. To overcome this problem, Fortran ignores blank spaces on a given line. In a do statement, you would have the word do, the statement number that is at the end of the loop, the index for the loop, an equal sign, and separated by commas, the starting value, the last value, and if there is an increment other than one, another comma, and then what that increment is. The problem is that if you are ignoring the blank spaces, it reads as if the variable is do101i, and you are assigning it the value of 1. It is only when you run into the comma that you realize you have gone too far. In that case, they would go back and scan just the DO, then scan for the statement number, then for the index variable, the equal sign, the start value, and the final value. Input and output, even file input and output, can be a time-consuming process, running much slower than the processor itself. This makes the buffering of input text crucial to the efficiency of a compiler. In most modern instances, input from a file is buffered by modern operating systems, rendering the issue less important than it was within the past couple decades. The code that you see on this slide is written in an earlier version of C, as it appears in the classic The C Programming Language by Ken Thompson and Dennis Ritchie. We are using the unbuffered file library. This depends on the programmer handling his or her own buffering. We have three constants. The number of bytes is 512. The number of bytes in a second on floppy disks used with the original IBM personal computer. We will use two buffers, so as we empty one, we are filling the other. We also have a stack of 2 characters, which is the largest number that we would look to push back into the input stream. We will be keeping track of how many bytes have already been read, the file descriptor, the input character, the position of the top of this very small stack, and the line number in the source code. The function ungetCH together with the macro getCh, allows the program to push and pop characters to and from the look-ahead buffer. If the top exceeds the maximum number on the stack, we will print the error message "too many characters ungotten" and exit. Otherwise, we push this character on the buffer. Open file gets one parameter, the name of the input file. We will then proceed to open it using the original I/O system that C had. We will give it the name of the file that is being opened for read-only. FD is essentially an index in the process's open file table. We would not expect to get a negative file descriptor. If that's the case, it meant we were not able to open it. We print a message to that effect and terminate with an error code of 1. The function closeFile, as the name implies, closes the file. It is written as a separate function to make later modifications simpler than it might be otherwise. Notice it has the system call close and includes as its one parameter the file descriptor. The function fetchchar uses two buffers, each of which is 512 bytes, and unbuffered I/O to fetch input one character at a time. We choose 512 bytes because this corresponds to a block in MS-DOS. Each time we reach the end of one buffer, it gets another 512 bytes until we reach the end of the file. The function has two static integer variables because we wish to save the value from one call of the function to the next. Nextchar is the position in the buffer of the next character to be read. This buff indicates from which of the two buffers we are currently reading. As we prepare to return a character, we need to see if we are at the end of the data in the current buffer. If so, we will start reading from the other buffer. Even though we only have two buffers, numbered 0 and 1, it is written in this fashion in case we decide to change this to a larger number of buffers. In the previous slide, we saw in that second if condition that if that happens to be true, it means we've reached the end of file. In the instance where we didn't reach the end of file, that means that we're going into a different buffer, and we're going to start with the first character appearing in it. The key words of modern programming languages are almost always reserved, meaning that they cannot be used by a programmer as an identifier, a user-defined variable, data type, or whatever. There are programming languages where this is not necessarily the case, making programs more difficult to understand and making it more difficult for the scanner to return the proper token. In the example here is taken from PL1. Then and else, which are keywords for obvious reasons, can also be used as variables, and in this case, we're making them both serve as Boolean variables. Now, the truth is in PL1, we don't use the term Boolean. They are actually strings of 1 bit each. In the example, if the word then has the value of true, then we will reset it to whatever value the Boolean variable else holds. If then was originally false, then we will set else to whatever value then holds. If you read it very quickly, if then equals else equals then, it's very difficult to make sense of that, and even if you read it more slowly, it doesn't seem to make a lot of sense. And it creates other issues when you are looking to determine which one of the two you mean. In a compiler construction course, the odds are very good that this may be the only time that you will actually write a scanner yourself. Scanner generators automatically generate a scanner given the lexical specifications and software routines given by the user. Scanner generators take advantage of the fact that a scanner is essentially an implementation of a finite automaton, and can thus be created in an automated fashion. Lex, which comes with Unix, is an example of such a software tool. Its equivalent in Linux is Flex.